So now let me look at a couple of examples and build our understanding based on the examples that we have. All right. So we have talked about, so I think we have 3 sections of properties. We've assumed that all of them have been fully studied and verified and studied. Okay, so today's material. We start with an example. Okay, we start with an example. If you remember, when we were talking about discrete time systems, we said that there is a discrete time system called a moving average filter, or in other words an averaging filter. So we go back to the moving average filter, MA filter. Okay, we are going to look at a causal version of a moving average filter. Y of n is equal to 1 over m plus 1, it's going to average over m samples, summation k equal to 0 through m x of n minus k. Okay, so it's 1 over m, x of n plus x of n minus 1, x of n minus 2 and so on. You're basically adding m plus 1 terms and then dividing by m plus 1 to get the average. Okay, so basically what we would like to do is to look at the behavior of this particular system and look at its the properties. So if I were to ask you to write down the impulse response of this filter, h of n, first task. Okay, please write down. It will be 1 over m plus 1, sample value of 1, and there are m such values. So this corresponds to 0, 1, 2, all the way through m. Okay, total, this is the number, impulse coefficient response number. So you can also indicate it by showing that this corresponds to 0. And because and after that it will be zeros. Okay, because it's a right-sided sequence, this is a causal system. Causal. Bibot stable, you can verify, it's a finite sequence, you can verify that it is Bibot stable as well. So this is what is called a moving average filter. And now we are asked to calculate the impulse response or the discrete time Fourier transform of this LTI system. So H E of j omega will be summation n equal to minus infinity to infinity h of n e power minus j omega n. We have a total of m plus 1 terms. So 1 over m plus 1 is a constant, I bring it outside, n equal to 0 through m e power minus j omega n. Okay, so you can see that it is it's in the form of a geometric series. So what you get is 1 over m plus 1, 1 minus e power minus j omega m plus 1. Okay, remember the exponent is the geometric series will be 1 more than the number of terms, and the denominator will be 1 minus e power minus j omega. Okay, this is h e of j omega. Now this does not give us too much of insight into what is the behavior of the system. So we will do some simplifications of this particular expression. So we are going to say that h e of j omega, I am going to just rewrite and simplify. The scale factor of 1 over m plus 1, we can leave it as it is. I am going to factor out from the numerator e power minus j omega m plus 1 by 2. Okay. I have taken out e power minus j omega m plus 1 by 2. So now what you will have in the numerator will be e power j omega m plus 1 by 2, because when you multiply with e power minus j omega m plus 1 by 2, those two will cancel and you will get a 1. Now the second term is going to be e power minus j omega m plus 1 by 2. Notice you got conjugate terms here. Okay. Similarly, you can, in the denominator also, we can take out e power minus j omega by 2. And what you will get here is e power j omega by 2 minus e power minus j omega by 2. Notice that you have it in the form of numerator and denominator, where there are a complex term and a conjugate term. So, the numerator can be simplified as 1 over m plus 1 is the scale factor, e power minus j omega by 2 and e power j omega m plus 1 by 2. So, we can cancel this term. So, this will cancel with the plus 1. Okay. So, what you will be left with is e power minus j omega m by 2, okay, because of the simplification. And the term on the numerator is 2j sine omega m plus 1 by 2. Denominator 2j sine omega by 2. Okay. So, of course, we can simplify the 2j and 2j cancels. So, now what we have is 1 over m plus 1 e power minus j omega m by 2 sine omega m plus 1 by 2 divided by sine omega by 2. Okay. Now, you may say that, well, you know what, this does not look like there is much insight into the system. Not quite. There is a lot of insight that we can get, and the purpose is to show you how to derive insights from this particular type of analysis. So, the first thing that we would like to do is look at a special case. So, we will look at the case where m equal to 5. And we would like to sketch this the behavior of this particular h e of j omega. This is what it looks like. So, again you can plug it into MATLAB or Octave, and you can do it. In fact, it's a very good idea for you to try and do that. You will see that the expression that we have here is one where we can look at it very carefully and look. So, at omega equal to 0, you get a 0 by 0 form. So, if you substitute using L'Hopital's rule, at omega equal to 0, we get h e of j omega. H e of j is 0 equal to 1. You can apply L'Hopital's rule and verify that this is indeed the case. So, when you plot the sketch, this will start at value equal to 1, and you will find that the first 0 occurs at 2 pi by 5. Okay, is that correct? Go back and look. So, if this value is equal to m plus 1 is m is equal to 5. So, 5 plus 1 by 2 is 3. So, and if you substitute omega equal to 2 pi by 5, you can verify that this is going to satisfy this condition. Okay, sorry, 2 pi by m plus 1. The first m equal to 4 is what we are doing. Sorry, that is why. Okay, m equal to 4. So, that is why so this typically will be at 2 pi by m plus 1 is the general form. You will verify that. Then you will find that there is a bump. This comes out to be at 4 pi by 5, another bump 6 pi by 5, 8 pi by 5. And when you look at the response now as it goes towards 2 pi, remember the periodicity with the period of 2 pi. So, basically you will see now whatever was there at omega equal to 0 will be there at. So, on the other side you can also see that the behavior will be identical. You will see this response at minus 2 pi by 5, minus 4 pi by 5, and so on. 2 pi by 5 minus 4 pi by 5 and so on. Okay, so this is a useful understanding to have, and this we can get only from the response that we have obtained. Okay, and this is if you look at it, it is allowing the low frequencies to pass, and all other frequencies all the way from 0 to pi. Pi is the high frequency. Those are between 2 pi by 5 and pi, that is getting attenuated. So, this is pi, those are getting attenuated. So, these frequencies are passed, okay, from minus 2 pi by 5. So, these are passed, and from here onwards they are attenuated all the way to pi. okay, attenuated. So this such a filter which allows the low frequencies to pass and attenuates the high frequencies is a low pass filter. So this would be a low pass filter. Okay, and remember, if you take M to be larger, what will happen? This low pass filter will become narrower, and you increase it further, it will become narrower. So basically, when you start averaging more and more terms, the response of this filter is going to become very narrow. And again, it's very useful to have the interpretation. So what is happening here? Supposing you think of a continuous time signal, or let's look at it in the context of a discrete time signal, x of n. Okay, x of n. Now, x of n has got certain samples. Okay, so think of it as an underlying signal which has been sampled. Okay, so let's mark these points like this. Okay, now what is the role of the averaging filter? And let us say that you have when this signal is very noisy, supposing this signal what you are having is very noisy. So when you sample, you are getting a sample plus noise. So what you do is you take a sample on either side. Take a sample on either side and do the averaging. What is the effect of it? It is like taking this signal and passing it through a low pass filter. What will the low pass filter do? It will remove those high frequency noise components. It will allow only the signal. And if you want to remove more noise, add more terms in the averaging. So the importance of averaging and what it does to your actual signal, how it removes the noise. The original signal is there is a lot of high frequency noise. The high frequency noise is removed because you are passing the signal through the low pass filter. The low pass filter will allow your signal to pass through, but it will attenuate the noise that are additional components that are there. Now, if I were to ask you what is the phase response of this LTI system, you may look at it and say, well, no, it's too complex. I'll have to go back and compute. Remember, you told me the formula is you compute the real part and the imaginary part and take tan inverse of the imaginary part by real part. Not quite. So look at this particular expression. You have HE of j omega, and notice which are the real parts here. Okay, this is real. This entire term is real. Okay, when you have a real quantity, what is its phase? Phase is 0. Okay, now the only part that has got the complex portion is e power minus j omega m by 2. And that is exactly the form in which the expression for the phase response is going to be. So what is the phase response in this particular case? Phi h of omega is equal to, remember what we said, e power j argument. So minus omega m by 2. You can write it down by inspection. This is the phase spectrum of this particular signal. What is the group delay? Tau h of omega. Remember, we have to differentiate with respect to omega with the minus sign. This will be equal to m by 2. And so it is very easy. I mean, basically from the original expression, we did a simplification, and the simplification helped us not only to get the magnitude response, but also to get the phase response and also the group delay if that is needed. Okay, so this is a useful result, and I hope you will be able to apply it whenever there is a need for us to do so.